In this unit we're going to cover web infrastructures, so especially with an overview on web-based architectures, especially related to authentication and access control. We'll have a look at some of the key protocols which might be involved in the next generation of web-based infrastructures, including Kerberos and SOAP over HTTP. We'll look at some scalable authentication infrastructures and protocols, and then also integrating scalable and extensible architectures such as using LDAP. Okay, so let's have a look at some of the key principles that the next generation of the web is likely to look at. And part of this involves what's called Identity 2.0. So with this, the internet and the web that we've created involves our identity being placed in many locations, and it's very difficult for us to actually control our own identity. The next generation is likely to be that the actual users themselves actually control their own identity and how it is released to parties on the internet. This is a major change for the internet, as the internet was created to be an infrastructure of computers, each with a unique IP address. The next generation of the internet has really been built around things, objects, such as people being part of this whole infrastructure. So if we have a look at this example, so we might find that this user here wants to control their identity. So in this case, they have various bits of information that defines their identity, and they might keep that in one location and then carefully control it. So in this case we can have a national insurance number, date of birth, bank account, business details, CV, and so on. So the bits of information of the identity that the user would want to release is that possibly in terms of tax, they would release their tax reference, their online login, some of the bank details, national insurance number, and date of birth. But they wouldn't release other details such as medical records, the location, work details, and so on. From a medical point of view, a medical practitioner may be interested in a home telephone number, if it's an emergency, some medical details, date of birth, and so on. So we can see here that the identity could involve many different elements, each of which can be given away to can be controlled by the user and given away as required. Another concept which is going to become key in the next generation of the internet is what's called SOAP over HTTP. The problem that we often have with systems is that they talk with different protocols, they use different data types, and it is often difficult to get an object from one computer on to another and for it to be still to be viewed as the same object. SOAP is a protocol which tries to reduce this problem, and what it does is to encapsulate objects, and this encapsulation allows the objects to be serialized onto the network and then sent over and then unpacked so that the same object is seen on the other side. So with this, SOAP defines an encapsulation process, normally around XML tags, and what we get is an envelope which contains the basic encapsulated data. So this shows an example here where we have a web service over here, and this client wants to access this web service, so it transmits the name of the web service and the value that it wants to actually calculate the square root of. So we can see here this is the web service and this is the actual value. This then goes to the service, is then translated with a square root method in this case, and then the result comes back. So we can see here that the encapsulation defines that the result coming back is in a double number format, and this defines the name of the web service involved. HTTP is normally used, as HTTP is typically allowed over most firewalls. We can also use TCP as our delivery protocol, which will generally be faster, but this can have problems because the TCP port on a firewall can often block messages being translated. Another problem that we can have with inside current systems is to be able to translate objects into a global hierarchical infrastructure. And one application layer protocol which tries to overcome this problem is LDAP. LDAP is based on the X500 directory format and uses a hierarchical infrastructure of entities. So this normally starts at the top level, and we can see here that the top level is UK, and then within inside UK we might have branches off. So this allows X500 to be extremely scalable into a global infrastructure. So in this case the top level is UK, then we have CO. We could obviously have other different domain names here, and then we can have Napier. So this is typically defined as the organization, the domain name here, and it fits into the internet structure. So we can see here that our domain name is defined as our domain controller is Napier, AC and UK. Then below that we can have an organizational unit, so in this case it's comp, and we define this in LDAP as OU, and then we can have a common name at the very end, so this itself is a user. So to access, say, Fred's folder, we might have an LDAP defining entity as Fred's folder as part of people in fake.com. We might have Fred's unique identifier for his login as UID as part of the people organizational unit, and then we might actually have the name of Fred himself. We can also use a URI to be able to reference objects from outside. I can see an example here of using the LDAP URI. This shows an example of how this structure is created. So we normally start off with a root object. So in this case we might have a root organization that then defines a number of container objects, which will then contain the actual objects themselves. So this shows an example of the root, and then we have the organization below the root. Then that splits into a number of organizational units, and then we can have users and devices, file systems and so on. The symbols that are typically used for LDAP include organization, and this tends to be one of the top level entities in LDAP. We can also have our organizational unit, as we have here. We can have a person, a location, country, and also aliases. So in this way we can build up a global hierarchy of things within inside an organization which map onto other trees. So this shows an example of our entities. So in this case we create our main organizational units. So in this case we've created one for people and then another one for groups. And next we'll map on our user ID on to one of these organizational units. So in this case we're adding a user login of Fred, who will map on to the organizational unit of people that we've just actually created, and he is part of this domain. Then we can define object classes for our login, our unique identifier, the given name, surname, contact name, telephone number, room number, organization, email address, his mail host, and so on, and even his home directory. So this allows us to be able to create a translatable and transferable format for the objects within inside our organization. And we can see another one at the bottom here, where we're actually defining a group, part of the groups, and this is given a common name of example. Now let's look at the main focus for this presentation, and that's to look at next generation authentication infrastructures. So basically what we have is that we have our person who might want to log in. That person obviously has some identity or identity credentials that they will use to identify themselves into the system. We might also have a device, and the device itself might have an identity, such as a digital certificate. It might have a MAC address, might even have an IP address, or even just a host name. The person might have biometric identity, they might have a username and password, and even they might have a soft token. They then pass this to the authenticator and define the service that they want to connect to. Normally we have a centralized authentication system, so the authenticator passes the details on to the centralized authentication server, which will then check the identity, such as checking with a PKI server for a digital certificate, or it might check usernames and passwords from a domain, such as a Windows domain. This obviously is a key choke point for the network and could be a single point of failure. So we often have more than one centralized authentication server. So if one falls over, then another one will take its place. Then, if the user is authenticated, they will then get rights into the domain and rights of access to services. So this is our generalized infrastructure for authentication. The traditional way to authenticate is typically with a backend Radius or TACAS Plus server. So we can see here. And what happens is that we have what's called the supplicant, and this is the entity which is asking for authentication. It then goes to an authenticator, in this case a wireless access point, which then typically forwards the request to the Radius or TACAS Plus server. It will then check with a PKI server for a certificate, or it might check for usernames and passwords from the Windows domain server. Once it has been authenticated, then the supplicant will then be allowed to connect to the network infrastructure and use services. We've now seen standard methods which are used for access to the network, and this is defined in the 802.111 802.1x layer, which defines a generalized method of access control for devices and users. In this way we can authenticate a user directly at the point which they connect to the infrastructure. And that supports a whole lot of authentication methods, such as LEAP, which uses usernames and passwords, but unfortunately has been shown to be fairly weak from a security point of view. We can have PEEP, which typically uses digital certificates. We can have SIM card authentication and so on, each of which can then connect to a wide range of network interfaces. So basically what happens is that when we have a starting request, a request ID comes back from the authenticator. This ID is then sent to the backend Radius, and then the Radius server authenticates the client through message interchanges. Along with this, the client needs to authenticate that the Radius server is correct, so we also get a communication between the Radius server and the client to identify the Radius server. After this, in a wireless network, we actually have a broadcast key which is sent to the access point to be forwarded to the actual client. Unfortunately, Radius has been created for a network type infrastructure and is seen to be fairly weak from a security point of view. So some of the threats that are involved, these include brute forcing of the user credentials. So this normally involves a malicious person continually accessing the Radius server, giving different user IDs and different passwords until eventually they get a success and they can actually log into the network. Unfortunately, Radius uses UDP, the UDP protocol, for its transport layer connections, which is connectionless. So there is no concept of handshaking of TCP packets. The packets are basically sent to ports 1812 and 1813. So it's very difficult for a firewall to pick off what is a valid Radius UDP packet and what is not. So it is open from outside to a denial of service against the Radius server. The problem with this is that if the quality of service reduces for the back-end authentication server, it can significantly reduce the performance of the whole infrastructure. Along with this, there is very little authentication built into the packets that are actually sent to the Radius server. So we can have the problem of a session replay, where an intruder, if they manage to capture the network packets, can actually play them back again into the network. There is also very little checking of the actual data packets for their identity. So we can get spoof packet injection, where an intruder might spoof their IP address into the network, so it looks like it's coming from a valid host. Then we get other problems such as a response authenticator attack and password attribute based shared secret attack. But one of the biggest problems, or the major problems with Radius, is that it is based on a shared secret key between the authenticator and the authentication server. So this can be distributed around a network infrastructure, so that if one of the devices is fairly weak, then it can actually reveal the shared secret key. Once that is known, then a malicious intruder can actually pretend to be a valid authenticator. The authentication infrastructures that we've created are typically focused on a certain organization, and more users are actually mobile and might be connecting from outside a network. So a key principle for the future is what's called Federated Identity Management, where we can use external systems to identify an entity which we can trust into our domain. So what this tries to do is it tries to divorce rights from identity, where a user will identify themselves onto a trusted system and then get some form of credentials which can then be used inside the organizational network to get some rights. So with this, what we can have is a federated identity management system where users can identify themselves onto a trusted identity provider. Of course, this will depend on the types of service they are actually requiring. So if it's something simple such as email, then they might just need to authenticate themselves onto Windows Live or onto Google. But if we require access to sensitive information, then we might need strong authentication, such as from VeriSign. So a federated identity management system will generally define the circle of trust. It is then up to these identity providers to focus on identifying a particular user. So an example that we have just now for a circle of trust is with OpenID. And with OpenID, what we get is that there is an OpenID account, and then that then leads to an OpenID login name, which has been generated from one of the OpenID providers. So in AOL, we get our OpenID name, Orange, Yahoo, and so on. And now Google is part of this infrastructure too, so that if you have a Google login, then it can provide an OpenID login name. So this OpenID account allows you to log in to a site using an OpenID account. We can see here there's a range of accounts which are supported by OpenID, so that you never actually have to give a username or password to the site that is logging onto, but what happens is that you are then forwarded into the domain, and then you must provide your authentication credentials to that provider, and once you have done that, then it goes back to the site and it can be logged in. So in this case, the identity can be stored in one place with a single password, and then multiple forms of identity provision can then be used. A more advanced and more scalable infrastructure is to use the Kerberos protocol. So with this, what happens is that we have what's called an identity provider, or IP, and an RP, or relying party. So the identity provider is separate from the relying party normally. So in this case, when the user goes to check in at an airport, they might provide their passport. The passport is then checked and a ticket is then issued. So that the user then goes to the relying party, which is airport security now, and then all they should need to provide for airline security is the ticket. So in this case, the security trusts the identity provider, in this case checking, to have done the identity provision correctly. So we can scale this up, so we can have multiple places that the user could go to check in, and we could even allow them to check in from different companies or even different airports that we trust. And then as long as they can provide the token, then the token will allow them to pass through airline security. So in this case, we define a trust infrastructure. So the way that Kerberos works, if we use a web service, is that the client contacts the relying party to define which service it wants to use. The relying party then provides the identity requirements that it requires and who it trusts, and that goes back to the client. The client then decides whether it can provide those credentials and with the right identity provider. So the user is then faced with the provision of selecting identity provider. After this, they will go to their identity provider and provide their credentials, which proves that they are that person. After this, the identity provider generates a token, and the token is encrypted and has a key, and also has a timeout on it. This is then passed to the relying party. The relying party then checks it and defines whether the user is allowed to use the service. The great advantage here is there doesn't have to be any communication, direct communication between the identity provider and the relying party. Okay, so we have some details of the actual exchange, which is in the notes, but this basically provides the basic encryption procedure for the whole of the protocol. A key factor in this is that although we're actually seeing the identity provider as one entity, there is actually two elements to it. There's an authentication server and a ticket granting server. But most Kerberos key distribution centers contain both components. Okay, so the basic protocol is here and also in the notes, but the first part is identifying the user onto the system, and we can have an independent ticket granting service. And then the second part obviously relates to the granting of the actual ticket. So Cardspace is one of the first examples of using a soft token to be able to identify the user. So in this case, the user can select, rather than using usernames and passwords, they can select the card, the identity they wish to use when they're logging on to the system, and they can use different identities for different types of logins. So in this case we have a personal card, and this personal card is really just created by the user. We can also have stronger cards, which are called managed cards, and these are used for online purchases and are backed up normally with a digital certificate and so on. The advantage with this method is that all the personal details, such as credit card numbers and passwords, are actually held off the computer. Okay, so this shows an example of us creating the cards. So we can have personal card, or we can have a managed card. So with a personal card, we can actually just pass our card that we've generated from our machine to the relying party, and then this is used to actually pass the login details for the user. So with Cardspace, what we have is that when we select a card or when we create one, we see all the cards that we have. Each card then has various details on it. Whenever we log in to an account which uses Cardspace, it will then prompt us for the card that we want to select, and then pass that into the system. Another key concept to allow for a more scalable infrastructure is the WS* infrastructure. So with this, There are common defined standards which use XML that allow protocols and messages to be interchanged. So there are three key elements to this. There is the identity selector, where the user can define how their identity is actually selected. We have the SAML language, which is a security markup language. We can also have security policies, and then we can have a back-end security token service. So with this we can either use the traditional PKI infrastructure with digital certificates providing the identity of objects, or we can have a Kerberos infrastructure. So the system is fairly flexible in that as we move from PKI towards Kerberos, WS Star can actually support this. So most systems are now moving towards this open WS Star, which includes a trust infrastructure. One of the core components of this is what's called the SAML language, which is a security markup language. And SAML involves defining a number of assertions. So these assertions relate to either authentication, and that asserts that a user has actually proven their identity, certain attributes which might define certain additional information about the user, such as LDAP attributes, and authorization. And with authorization, it actually makes assertions of to what a user can actually do. Then we have the protocol, and the protocol typically is SOAP over HTTP, which is the most common method just now. And then we have the basic binding. So the bindings normally happen through SOAP messages. It is also possible to use TCP, but more often we use SOAP over HTTP. So one of the advantages of this infrastructure is the concept of single sign-ons. So with single sign-ons, then we can actually redirect users to an identity provider, so that the authentication of the identity doesn't actually have to happen inside the service provider. So in this case, the user logs onto a service. The service provider generates a SAML request. It is then sent back, and there is a single sign-on URL which the user is prompted to in order to identify themselves. So then the user is then redirected to the single sign-on with the SAML request. The SAML is then parsed and a new SAML response is generated by the identity provider. And obviously the user needs to identify themselves at this point. So the encoded SAML is sent back, which is then forwarded through to the service provider. The SAML is then checked, and then the access is granted to the service or not. So single sign-on is an important concept. So then once we've been authenticated onto a system, then there needs to be a mechanism for access control. So this will be covered in more detail in a following lecture, but we'll look at some of the basic principles involved in access control. The three main methods that we can have for access control are for role-based security, and with role-based access control we define a number of roles inside the organization, and then users will join those roles. The access and the rights that are granted are then based on the role that they actually have. So this tends to simplify the overall security policy, and we obviously want to minimize the number of roles that we have so that we can simplify the whole of the infrastructure. Then, if we are connecting between domains, we might expose certain roles to another domain, and then if we've identified ourselves externally to a third party through an identity provider that we are part of that role, then we might be trusted into another domain. This gives us inter-domain rights. Other types of access control that we have are based around the operating system. So in this case, the rights that we get are granted purely by the operating system and not necessarily by our roles. So it's typical with inside Windows and Linux, where the operating system grants us rights onto the system. This is known as mandatory access control. Other systems define what's called discretionary access control, and in this way the user or the owner of the entity actually grants rights to other entities. So this might be in the form of medical data, where a patient might grant access to a GP or a consultant to be able to access their rights. If they want, they can then revoke those rights to the data. This is known as discretionary access control. Okay, so we've covered web, an introduction to web infrastructures, especially trying to highlight some of the new protocols that are involved and how we can scale our existing architectures.